AB Calc, section 3.2. Goals of this lesson are as follows: relationships between the graphs of f and f prime, graphing the derivative from some data, how might the derivative fail to exist, differentiability implies local linearity, derivatives on a calculator, differentiability implies continuity, and some one-sided derivatives. Lots of stuff, but we're going to actually pack that into 4 slides. So let's look at the relationship between the graphs of f and f prime. So we're going to graph the derivative of the function f, whose graph is shown below. So we're going to say that this black graph is f of x. And we're going to graph the derivative based on the slopes of f. So you can see on this interval, from negative infinity up to 0, the slope of this graph is up 2 over 3. So the derivative will equal 2/3 on that same interval. Okay, that's supposed to be a horizontal line. So the output when f of x is increasing, notice that f prime of x is positive. Okay, so let's look at the second interval. Here's the interval from 0 to 3. The slope here is -1. Thus, we get a horizontal line at y equals -1. As you can see on this interval, since f of x on this interval is decreasing, it's got a negative slope, the derivative function is less than 0. Now, of course, we're going to see on the third interval that the slope of f of x is positive. And it looks like it goes up 1, 2, 3, 4. Oh boy, that should be, 5 and over 2. So the slope of the function f of x is 5/2, which is equivalent to 2.5. So on this interval, the derivative function looks like that. So again, f of x is increasing, therefore its output is greater than 0. Okay, let's look at example 1. We're going to graph the derivative from some data. Actually, we're going to graph the function. So we're going to sketch the graph of f of x that has the following properties. First of all, f of 0 equals 0. So let's check this off. F of 0 equals 0. There's the point 0, 0. Okay. Actually, I don't think I wanted to put it right there. I'm going to put that, let's go right here. You'll see why in just a second. Okay, it looks like the slope of f, right, f prime to the left of +1 is -1. That means that the function f has a slope of -1 when x is less than 1. Okay, and the blue portion of the graph represents the slope when x is greater than 1. So it looks like the slope is 3 when x is greater than 1. So I'm going to connect, and this is f of x if the original graph was f prime of x. Notice that f has to be continuous for all x. So we've graphed the derivative, and we've ensured that f is continuous for all values. Now, let me reiterate here. Here is f when x is less than 1. It's linear, right? It's linear. It's got a slope of -1. So f prime is less than 0. It's -1. The output of f prime is equivalent to the slope of f of x. Let's write that down. The slope of f of x is equal to the output of f prime. We knew that, right? That's just putting it in a different context. Okay, let's continue. Okay, example 2 here is saying to show graphically as well as analytically that the following function has left-hand and right-hand derivatives at x equals 0, but no derivative at 0. So I'm going to graph f of x. F of x is going to be x squared. Let's put that in one color. X squared when x is less than or equal to 0. And 2x when x is greater than 0. Okay, so notice that there is a very abrupt change in slope. So you can see that the function's slope is approaching some value. It's negative, smaller negative, smaller negative. Looks like it's approaching 0 here. And then all of a sudden, boom, there's a change. And then the slope of the function becomes 2. So we're going to use limits to show that the function has a left-hand and right-hand derivative at x equals 0, but no derivative at 0. Okay, so let's work that a little bit. So let's find the derivative coming from the left of 0. That'll equal the limit as h approaches 0 of f of x plus h minus f of x all over h. Okay, one minor thing that I need to add is that h is approaching 0 from the left. That indicates that we're looking at the derivative of the left portion of the graph of this piecewise function. Okay, so let's do a quick evaluation. And actually, I also goofed something else up. If we're finding f prime coming from the left at 0, we should plug in a 0 into the function as well. Okay, so the derivative coming from the left of f of x at 0 will be the limit as h approaches 0 from the left of f of 0 plus h. So if f of x equals x squared, f of 0 plus h would equal 0 plus h squared. Okay, and f of 0 would equal 0. Therefore, I would have h squared minus 0 squared all over h. So the slope coming from the left would be the limit as h approaches 0 from the left. And notice this will be equal to h squared in the numerator and h in the denominator, so I can reduce, and I would get the limit as h approaches 0 from the left of h. And notice then that I can do a very simple evaluation of that limit and see that the slope equals 0. So the slope at 0 on the green portion of the graph is approaching 0. Okay, so that slope. Now let's work the other side. Let's look at the slope on the right-hand side. So that'll be f prime coming from the right at 0, which will equal the limit as h approaches 0 from the right of f of 0 plus h minus f of 0 all over h. Now, in this case, f of x is equal to 2x. So f of 0 plus h would equal 2 times 0 plus h. And f of 0 will equal 0. Therefore, the slope of the function coming from the right will be the limit as h approaches 0 from the right of 2 times 0 plus h, which is 2h, minus 0 over h. So the derivative, or the slope, of the tangent line as x approaches, at x equals 0 is the limit as h approaches 0 from the right of 2h over h, which is equal to 2. And therefore, we see that the slope of the function f of x coming from the right at x equals 0 is equal to 2. Okay, so we have identified, I'm going to just sketch the slope of that tangent line, which is equal to 2. We've identified that there are two slopes, a left-handed slope, or a left-handed derivative. Here's your left-handed derivative. And then a right-handed derivative. Here's your right-handed derivative. But those derivatives aren't the same. Now this might remind you of continuity, and it should. Okay, we're going to start talking about the continuity of the derivative, which is called differentiability. We'll get to that in future lessons. So, does a function have to be continuous at a point to be differentiable at that point? And the answer to that is absolutely yes. Okay, what if the function is continuous at that point? Must it be differentiable? The answer to that is no. Right? So think of examples and counterexamples. All right, so let's talk about where derivatives fail to exist. Okay, we noticed in this example, right, we saw a sharp change in slope, not a continuous, smooth change in slope. So let's read this and talk about some of the differences. A function will not have a derivative at a comma f of a where the slopes of the secant lines fail to approach a limit as x approaches a. I was talking about continuity of derivatives earlier. That's exactly what that's talking about. An otherwise smooth function will fail to have a derivative f prime at a point where the graph has a sharp corner. For example, the absolute value of x. Absolute value of x has a discontinuity in its derivative or is not differentiable right there. Right, we've got an abrupt change in slope. All right, another one is a cusp. All right, so a cusp, an example of that, is the graph of the square root of x. And, whoa, that was a good attempt, the square root of negative x. All right, clearly this point right here, also a cusp. It's not differentiable at that point. How about a vertical tangent? A vertical tangent looks like this. Here's the graph of the cube root of x. All right, right here, there is a vertical tangent. Therefore, the function is not differentiable at that point. And then any discontinuity, either a jump or a vertical asymptote. So this function, the square root of x over x, actually looks like this. It looks like that. Okay, clearly we've got a discontinuity here, right? We get a problem, therefore also not differentiable. Okay, let's move on. I think we got a couple more slides and we'll get to it. Okay, so example 3 says find all points in the domain of f of x, which equals the absolute value of x minus 2 plus 3, where the derivative f prime does not exist. Now you don't need to know how to find the derivative function at this point. All that you need to know is that with an absolute value at its vertex is where it will not be differentiable. So its vertex can be identified based on the transformation that's going on. So the parent function, absolute value of x, which looks like this, has been shifted to the right 2 units and up 3 units. Therefore, to the right 2, up 3, no change at all in its orientation. Therefore, the function f of x is not differentiable at x equals 3. Okay, just get used to absolute values, square roots, and really any other function that's put together in a piecewise fashion. All right, there are others, but we'll get to those later. Most functions we study are differentiable for all x. This symbol right here means all x, and are smooth and continuous in their domain. All right, so the next idea is local linearity, which just means differentiable functions are locally linear if we can zoom in far enough and the curve will become closer and closer to a straight line. Okay, kind of unrelated. Let's move on to example 4. It asks, graph the function f of x equals absolute value of x plus 1. Okay, let's sketch it. That's the absolute value function shifted up 1 unit. Okay, where this is 1, and this is 2, and this is negative 1, and 2 as well. It asks for f prime at 0. Well, f prime at 0, we should know now there is no derivative that exists there, right? Because that is at the vertex of an absolute value function, right? It's at a point where the slope changes from -1 abruptly to +1. Okay, let's start talking some calculator stuff here. So derivatives on a calculator. Syntax for your calculator, math 8, right? If you press the math button, right, if you got a traditional graphing calculator, you got your screen, your math button is right about here. It's a couple buttons below the screen. All right, if you press math and then the number 8, you'll see this notation. Okay, it'll say numerical derivative. What you want to do is you want to plug in f of x, and then the letter x, which will be the variable for which you are differentiating, and then the x value at which you want the derivative. So if I wanted the derivative of, let's say, f of x equals e to the x at, so find f prime of x at x equals 2, right? I would press math 8. It would come up with this notation, numerical derivative. That's not perfect, but I don't care. E to the x, and then x, and then 2. Okay, and then I'd press enter, and it would give it to me, and I'd have the slope immediately. All right, so it says find the equation of the tangent line at x equals pi for f of x equals sine squared x e to the x. Okay, so the equation of the tangent line requires two things. It requires a slope, and it requires a point. Okay, the point that I'm going to have is x equals pi, and then whatever the output of f of pi is. So f of pi, let's figure out what that would be. That would be sine squared of e to the pi gross. I don't know what that would come out to be, and I don't really care, so I'm going to write it as that, sine squared e to the pi. Okay, that's my point. I just need my slope. Now I've got to use my calculator. I'm going to do that right now, live and in living color here. So I press math 8, and my calculator is high speed, so I actually typed f of x into y1. So I'm going to take the derivative with respect to x of y1 at the point x equals pi. And it gives me a value. It spits out the number 17.2636. And I'm going to round that to 17.264. This is a perfect opportunity for me to let you know that any values that you calculate, your final calculation should be rounded to 3 decimal places. Okay, so I'm going to write the equation of the tangent line, which would be y minus sine squared e to the pi, which I suppose could be written in decimal form. I'm leaving it like that. Slope 17.264 x minus pi. There is the equation of the tangent line at x equals pi for f of x. Okay, let's look at example 6. Looks like a calculator allowed problem. We got a nasty function, y equals e to the tangent x minus 2, crosses the x-axis at one point in the interval there. What is the slope of the graph at that point? Okay, so this is a little bit more involved. What it's going to require me to do is find the point of intersection. Okay, so the point of intersection of y and the x-axis. Okay, first I've got to do that, and then I've got to find the slope of the function. I've got to find y prime at whatever that x value is. Okay, so I want to know when y equals 0. So what I'm going to do on my calculator is in y1, I'm going to type e to the tangent x minus 2. And I'm going to go to my calculator, right? And I'm going to graph. I'm going to set my window. Let's talk about window real quick. I'm going to take an x min of 0 and an x max of 1. Why? Because of this interval. I'm going to take a y min. I don't really care what it is, but I'll go -1, and a y max of positive 1. What that'll do is that'll give me this window here. And I'll go from, and I'll have something that kind of looks like this. Okay, so here's my x-axis, which will go from 0 to 1, and my y-axis, which goes from -1 to 1. So I should be able to see the function show up when I graph it. All right, I'm going to graph it off video, and then I'll come back and talk about it. Okay, so a couple things before I get into this. Always make sure that your calculator is in radian mode. So press mode, go down a couple spaces, and make sure you're in radian mode. What I get here is a graph that kind of looks like this. Okay, so I'm seeking to find this value right here. And how you do that is you press second trace while you're looking at your graph, and you go to option number 2. It says 0. And it'll prompt you with a left bound, right? And the cursor will show up over here. You want to get it to the left of this point, and press enter, and then it'll say right bound, and you want to move it over here to the right side of that point, and then it'll say press enter, and it'll say guess, and you don't guess, you just press enter a third time, and then it'll give you this value. So I get a value for that x value to equal, what is it there? Boy, I think it was like 0.606. Okay, yeah, it was 0.606 and then some change. So I think it was 0.6 and another 0.6 and etc. Now I'm going to store this number. I'm going to press stow. That button is right above the on switch, or the on button for your calculator. So I press stow, and I'm going to store it by pressing alpha, and then the math button. And the math button will give you the letter A, okay, which will give you A. So I'm storing it as A. All right, I want to find the slope at A. So go back to your home screen and press stow alpha A, and it will store that value. All right, so you now have that value stored as A. What I want you to do is press math 8, and dx, plug in y1. Okay, so the way you can plug in y1, like my calculator right now looks like this: d box of box equal to, at x equals, fill in the box, right? I want to plug in, just type in an x here. I want to put in y1 here. Okay, so this is going to take the derivative of y1 and evaluate it at A. So the way that you get y1 right here, quickly at least on a newer calculator, is press alpha. Okay, press alpha, and then press trace, and then select y1. Okay, that'll pull your function up so you don't have to type it in again. Okay, and then I scroll over here to this blank and press alpha A, and you will get your slope. Now your slope in this case can be rounded because we're not going to have to use it again, so I would have 2.96, I have 0.9, so I'm going to round that to 2.961. All right, so now I have a slope, and I have a point. That point was right here. X equals 0.606, and y would equal 0. Therefore, oh, hold on now. What is the slope of the graph at this point? I didn't even need that. All right, so the slope of the graph at that point I have right here. It's 2.961. All right, so I got a little carried away there, but some of those calculator instructions are very important as we move forward. Okay, let's keep moving. One more slide here. All right, so a little bit of talking, not a whole lot of writing on this slide, but I wanted to talk a little bit about one-sided derivatives. So for a function to be differentiable at a point, the slope from the left must equal the slope from the right. That reminds us a little bit of continuity, right? Hence, the derivative from the left must equal the derivative from the right. Symbolically, we've kind of looked at this already. We said the limit as h approaches 0 from the left of f of c plus h minus f of c over h needs to equal the limit as h approaches 0 from the right of f of c plus h minus f of c over h. So differentiability implies that continuity needs to be present. All right, so theorem 3.1, differentiability implies continuity. If f has a derivative at x equals a, then f has to be continuous at x equals a. So if a function is not continuous, for example, this function here, oh, that was odd, this function here, all right, it can't be differentiable. Can a function be continuous but not differentiable? Sure, right? We talked about that on the previous slide. That's a continuous function, but it's not differentiable right there, right? But what if a function is differentiable? Hey, it's smooth everywhere. So if it's differentiable, it's got to be continuous. All right, so let's talk about, finally, the intermediate value theorem for functions and derivatives. So we remember the IVT, right? IVT says if the function is continuous on an interval, the function has to take on all points in between f of a and f of b within that interval, right? At least once. Now, there might be points that are outside of the interval of the original outputs, but it takes on all values between the two at some point. Theorem number 2, the intermediate value theorem for derivatives, says that if a and b are any 2 points in an interval on which f is differentiable, then f prime takes on every value between f prime at a and f prime at b. This implies that f of x has to be continuous. So let's look at a quick sketch. Let's say that we've got a and we've got b, and the slope at a is 0 and the slope at b is 1. Okay, so f prime at b equals 1 and f prime at a equals 0. So f prime at c has to be between 1 and 0 for at least one value c, right? It's going to take on all slopes between 0 and 1. It can't just skip a slope, right? Then it wouldn't be differentiable. So here it's 0. Okay, so maybe here, not well sketched, but maybe it's 0.1, and then it's 0.11, and then it's 0.17, but it's continuous. The slope is changing continuously and taking on all values. Now here, of course, it looks like it's steeper than 1, right? So it might look like the slope's 1 here, and then it goes a little higher, but then it comes back down, and then it comes back up to 1. So it's hitting all slopes between 0 and 1, and possibly others. Okay, that is the intermediate value theorem of derivatives. All right, guys, that's it for 3.2. See you in the next video.